beautiful thing.
All right, everybody got a seat, got your coffee. Good morning, everyone. My name is Manesh, I'm your host. Thanks for joining us today, great talk here. I want to introduce Garren Staubli. Garren is a senior data engineer at Blueprint Technologies. He has been specializing in Apache Spark, been doing this stuff for the last 3+ years. One of the few guys that I know that has actually built production applications using Spark structured streaming to do real-time machine learning. He's also built some of the stuff for something called iSpot.tv. So good stuff and a great talk here. So Garren, over to you.
Thanks, Manesh. Morning, everybody. My name is Garren, solution architect, senior data engineer at Blueprint. I'm here to talk to you about structured streaming with machine learning to build a real-time decision engine. So they made me use a template, so this is just my actual slide. You can go to my website. I try to keep all of the, I made all the slides available. If you want to use that, you can just grab the whole slide deck so that you don't have to worry about taking pictures or anything. You're free to. Nothing here is proprietary. So am I qualified? As Nick Wilde from Zootopia would say, no, I'm not. But actually, I have worked with Spark for a few years, been in the big data space for a number of years, and actually I worked with the Q-Ball guys like Manesh for quite a few years. We go way back. Done a bunch of real-time big data reporting. Now I'm working on a real-time decision engine using structured streaming and ML. That's why you're here. And if you're not, then I'm sorry. So maybe I'm qualified. So here are our objectives today. I like to come up with acronyms because I know that we don't have enough acronyms in our industry and in the world at large. So I came up with SPOAL because we're going to go over the Spark 2.3 streaming features. Then we're going to talk about the problem itself. It's for a client that I'm working with right now. The options for the solutions that we could come up with, the architecture overview, and the lessons learned from that. So first, let's talk about streaming. So right now, when you think about streaming in Spark, you're reading from a place like Kafka, and you're going to pull in the data, process it, and then you're going to write it out somewhere. But often you have two different data sets that you want to work with, whether those are, say, you have an add event, and then you have a click, and you want to link those together. Until now, until Spark 2.3, which just came out at the end of February, you couldn't actually join those together in real time using structured streaming. But as of 2.3 and at February 28th, that's when it was officially released, you can actually do stream-to-stream joins. And so now you're going to buffer the data on both of the sides, you can handle late events, and we're going to talk more about this. And it's using the same join semantics as if you were joining a stream to a static data set or a static to a static still. Another one of the cool features that 2.3 brought out also is continuous processing. So before continuous processing, you've got this really happy kid who filled his super soaker up with some water, squirted the water, and so that's micro batching. That's when you just have this little bit of water and you're squirting each time. So that's when the data's coming in, you pool it up, you shoot it out. But this kid is no match for continuous processing where you get millisecond latency. I mean, he's just going to get rocked. So he's not going to be a happy camper anymore. But that's okay because continuous processing is super awesome because you go from 1 second or so latency with micro batching, which is what Spark is most known for. It's one of the main criticisms that has been out there with regard to Spark, say from Apache Flink, is you have micro batches instead of actual continuous processing where you're actually iterating over each item as it comes through. So continuous processing is really cool. So the problem definition. You have a user on a site. They do a search. They get some results back. They choose option 3. We have some logs coming through. I call them alpha and beta. Obviously, as you can tell, it's a little bit proprietary, so I can't give you the details of what all these different elements are. But fundamentally, that's the basic flow, is a user, site search, streaming logs. So now we know that that's our base condition that we're working with here. So the normal way, so these are now, we're going to go over the options. What are our options for solutions? We're most familiar with batch rule generation, where we're going to maybe run a scheduled job that's going to look every, say, hour and create some rules to say, okay, well, based on these different search criteria, we want to move the positions around, the ranks around, so that option 2 becomes the first one so that people are more likely to click on it. Because if we look back here, I put just relatively random numbers that would indicate kind of the propensity to click on any one of those. So 55%, they're most likely to hit number 1, 30, 15. So we really want to make sure that the best result is at the top, fundamentally, because that's the most likely to click. So every hour or so, we might run a process to generate some rules, or every day, to then create the rules and apply them so that now our site can get updated and we can start serving those changes and hopefully get better conversion rates, better engagement, who knows, it depends on the business metric. So here are kind of the pros and cons of a batch rule generation. You've got nice, straightforward, scheduled-based deployment, a simple architecture, because obviously now you have very simple, you're just reading in from some data source, doing some processing, and writing out your rules to tell what you want to do. And it's pretty low cost, because you're only running this every hour, every day, so you don't really have a high cost burden here, and just not as much to worry about there. But the cons are pretty significant, and I think in a lot of ways, we as an industry are going to start addressing a lot more of these, and that's you have a really big delayed response. You're reactive, and the impact is a lot lower because you're not making those changes in real time. You're not affecting the user and affecting their behavior on the site, and you're not affecting similar users like them in a similar audience. So as you might guess, we're going to talk then about the streaming option. So we're going to look at things in a real-time perspective instead. So now the pros kind of are kind of the opposite of the cons here. So now we're going to do real-time adjustments. That's obviously our primary goal here. We're going to be much more proactive so that now when the user comes through and they're about to get the site loaded, or even after the site has been loaded, we're going to learn from that and try to immediately send them the right results, either that time or potentially the next time, and similar users like that, so that we can learn as fast as possible and make those changes in real time. And it's much more impactful, because now we're not waiting on events to then decide what to do. But there are some cons still. So now we require a lot higher durability, because now our process is going to be running all the time. The architecture gets a little bit more complex, because anytime you have a streaming application, it's going to be more intensive. And we also need 24/7 monitoring, essentially, because these are running 24/7, so therefore they're going to be impacting our business 24/7. Therefore, we need to be watching it at all times. We need to have systems set up to keep track of it. So this is the really fundamental high-level architecture, where we have our two different data sources coming in, streaming. We're joining them into what I created, kind of a new little gang symbol, theta. It's just alpha and beta together. Then we're gonna throw that through some of our machine learning models, and pass those final results, those rules, if you will, off to the live site change API, which will then, as you can tell here, I don't think I have a laser, do I? Anyways, you can tell that option 2 is now on the top instead of on the bottom, or instead of in the middle. So now the critical part is we learned, because of our stream in real time, and we made that change in real time to move option 2 to the top so that we could increase the likelihood of clicking on that. So fundamentally, then, this is what we're looking at. So now we're gonna go into the depth, and you're gonna see that architecture becomes extended, because we're gonna keep going through this. So the way that the data comes in from the start, we're starting at the beginning here. We're starting from Kafka and how it gets to Kafka. We have an app or a browser. It has metrics, logs, and events. It sends it through a collector system. That gets sent to Kafka, but if you'll notice, it also has a T-pipe out to S3. So S3 is partitioned by date and time, and they're less than 50 kilobyte gzip JSON files, about 1 million per day. If that doesn't give you cringy feelings, I'm so sorry, but we are going to address that problem because that is fundamentally very painful for anybody who works with data, is to deal with small little files. It's the infamous small files problem. Kafka has we have in our alpha stream, we've got 48 partitions, 2 replicas, 24 in beta and 2 replicas, and it's just streaming JSON. So fundamentally, let's just say that this is what it looks like. And of course, because I like food, I chose a donut version of this. So as you can see, this is nested JSON, where you have batters is now a structure that has different batter inside of it to say regular, chocolate, blueberry, or devil's food. And if you look really closely, you can see that I really like blueberry. But we don't actually want to work with this in the nested version. We want to work with this in the flattened style. So we're going to go ahead and go through a flattening procedure to take the nested version of the batter information and flatten it so that we can then do a join on similar data that we get from our other stream. So, warning, if you like Scala, happiness just ahead. If you don't, you've been warned, it's coming. We're going to go through a little bit of Scala code to show you how I'm working with this and how you can do the same thing. So at the top here, we have case classes. They're nested, so you can see that the pastry record has sequence of batter. That's what the top one is. We're going to then use that to read it in, and you're going to see why we're going to use that in a second. So the first part here is we're going to use the encoders.product to actually create a schema out of that nested record. So that if you look on the side, you'll see the actual JSON, and you'll note that the case classes match up with the JSON. And if they don't, I'm sorry, because I didn't actually run any of this. But fundamentally, this is what you do. So once the schema's been generated, now we're going to use that later on. And so first we're going to take so what I need to clarify here. If you'll note df here, that little variable is a streaming data frame. So it's using spark.readStream in order to read in the Kafka data coming in from one of the sources in this case. And so now we can run just basic Spark transformations on it, like select expression. And in this case, I'm going to cast the value that I'm getting back from Kafka as a string. And I'm just going to call that new column JSON string. Then once I have the JSON string just as a blob of a string variable, sorry, whoops, wrong button. Then I'm going to use the Spark SQL function, as you'll note I import right here, to take that JSON string and convert that, or to actually start parsing it. Because right now it's just a string, but once I pass in from JSON and I give it the column name, and then I give it the schema, it's actually going to parse that. So that now I fundamentally have a true JSON structure that I can start playing with. Then here, the third bullet point, I'm going to take that structure, and so right now it's just one column. So I would have to access each element of that string, of that JSON structure independently. But by doing .star on that JSON structure, I now make all those elements of the JSON top level. And then finally, depending on how familiar you are with Scala or Java and Spark specifically, one of the main ways to work with Scala and Java, especially if you're using Spark, is using the dataset or data frame APIs. If you use Python a lot, you're familiar with data frames, I'm sure, extensively. If not, become familiar, because they're much better than using RDDs directly, especially with Python. But in the bottom here, I'm going to so we started with a JSON string coming through from Kafka, and we're going to end up with actually a custom object of pastry record. So we're going to have data set of type pastry record is what our final object will be. And I don't know about you, but that makes me kind of hungry. So next, we're going to talk about the actual stream-to-stream joins. And the first part of that is something to really consider when working with a streaming application. And that is, whenever you're doing streaming, you're going to create a pool of data on one or both sides. So in this case, we're talking about two different sources. So you have to create that pool of data from which you can join, because events are going to arrive late, they're going to arrive disordered, but you need to be able to still join them to your other data set. And if you think about it, there's risk for that data, that pool, to grow to such a large extent that you actually run out of memory, you run out of space. You cannot function, your system cannot function if you're using too much of the machine. So that pool, just think of it like a dam. You've got all the water coming in, you're damming it, but you're letting the water fill up so much that it actually starts overflowing. And okay, we're in Arizona, we're not in California, so at least that's not as much of a problem here. But in other places, there is a risk of the water flowing over and destroying your dam fundamentally. And you don't want that. So we're going to talk about unbounded. This is the start. This is the default. If you don't know any better, or you're just getting started, you're going to start with an unbounded join, or an unbounded stream, where that pool of data that you're going to be amassing to do your join there's no limit. It'll just grow unbounded, and eventually, presumably, you'll run out of something, memory most likely, over time. And if you look closely, you'll see that line is linear. Every second that goes by, just more keys that it has to keep track of, because it needs to keep those in memory so you can keep doing your join. But there, of course, is a solution to this, and it's bounding with watermarking. So now you'll note that it's a similar linear progression, except now you give it a time condition, where the data that comes in, if it's, say, more than 10 minutes late, you start to just throw out the data that's old. So that now, as your pool gets bigger, you have a release valve that pushes the data out that you no longer need. Because you know that's too late for you, and you need to have a limit as to when data can come in. You don't want to be processing join data. You don't even want to be holding in memory join data from 2 months ago, because you're leaving your streaming query running for 2 months. So use bounded with watermarking, don't use unbounded. Very clear, right? So then there's the machine learning aspect. I know I definitely can't go into the deepness of what it's doing specifically here, so that's why this one's a little bit boring. I'm sorry about that. But it's using Spark ML, and it's important to me to note it's using the .ml. It's not MLlib that people might be familiar with. MLlib, Spark has a tendency for kind of odd naming systems. But ML, I specifically point out that it's spark.ml. And that's the data frame dataset-based machine learning library within Spark. It's good to use this because you'll get better performance, and you'll get better performance in general by using data frames and data sets instead of RDDs. We're using XGBoost and/or random forest regression, depending on what we're trying to accomplish. It's trained offline right now, and we're planning on keeping it up to date over time, so we'll retrain it as we need to. And it's served directly in the stream, and we're just predicting future value out of it. So then when we actually want to take action with this, so sorry, I forgot to put the warning slide up. Hopefully you don't mind. Scala code. So we have a data set. We're going to write the stream. And what's different about this approach that I really want to point out is, instead of taking a more traditional approach of writing to, say, Kafka again, or writing to a file system, this is going to let us create a for each writer. And a for each writer is the concept of, it's going to iterate every row that it sends out, that it writes to the stream. It's going to open a connection. So that's what you'll note, by the way, I just copied this code directly from the Spark base, because that's awesome. I mean, that's like half my life is copying code from other people. So we're going to open this connection, and now we can really do whatever we want with the data. We don't have to pipe it out to Kafka and then have some other consumer that then reads it and then actually acts on it. Now we can write, in this case, directly to an API that will immediately make changes for the user. So if we put this all together, that means you can go from reading data in through Kafka on, in this case, 2 different streams, doing your machine learning, and writing those results back to the stream, to the API, to ultimately make the changes to the site. And if you do that using continuous processing, theoretically, you're talking about milliseconds between the start of your job and when the API gets the hit. So let that sink in for a moment, just how quick you can make changes and use machine learning to make those direct optimizations to your site and to your consumer base at large. So once we open the connection, then this is just a template. Think of it as an abstract. You have to ultimately implement these 3 different methods in your for each writer in order to actually get the results you want. But fundamentally, the sweet part about this is you can do whatever you want with it. So you can write those results out and make that impact in real time. How am I doing on time? Okay. So infamous small files problem. Bye. Thank you, InSync. I had to put that in there. I got a little bit funky with my visuals today. So that's the concept of reading data in from a million different small JSON files every day. Spark just can't handle that. No system really likes to work with large amounts of small files. Every system likes to have a more optimized structure, whether that's Parquet files, which I'm a big fan of, ORC, or even just bigger JSON files. One of the things that I particularly don't like about JSON is that it has a very high cost of parsing. It takes a long time to parse the data that comes through. So that's why I usually tend not to use something like JSON. So let's tell them to stop. But what we learned also is that we can parse that JSON data, and we can use nested case classes to make the JSON from just this kind of crazy unclean string, if you will, into custom Java objects or custom Scala objects, depending on what context you want to think about this in, and make our life a lot more sane, because now we can take what used to be unstructured, relatively semi-structured JSON, and now we have real objects that we can point to, and now we can do true static typing of our work, which I'm sure anybody who writes in Java here, Scala, anybody? Okay, perfect. So you all are probably nodding like, yes, I can still live, because you don't want to work with dynamic data sets where who knows what strings you've got available. So we used encoders.product to actually get the schema from the case classes that we defined. Then we finally converted it to a data set so we could actually do the custom object and typing. So this is Eeyore. He's really sad because he doesn't like to parse JSON. And he's from Seattle, because obviously the rain cloud, if you didn't get that. But let's make him Tigger. Like I said, I got a little visual happy. So operations. This is definitely one of my favorite memes of all time. Partly because my daughter would probably do that exact thing. So one of the key parts about streaming applications is that they're always on. That means they need to be durable. They need to be constantly reliable. Sorry, hydration break. Now, what that means is, instead of like a rule-based system where every day you're writing some new result, just writing some new rule out, the streaming job in our case that I was describing is very critical to have it always working. Because if it's not always working, who knows what your results are going to be? And if you don't have it built for high durability, high reliability, you never know really how your end user is going to be functioning. So it either needs to be constantly running and constantly working with full monitoring, full testing infrastructure, or you need to have some fail-proof like fallback that you can drop back to and say, okay, my streaming system that's creating my rules and changing my customer experience and really improving their overall flow is not working right now. So I need to fall back and just go to a rule-based system, or I need to go to a just default state of time. And monitoring is important as well. So this is just a screenshot that I took, or that I grabbed, that just shows the system load, CPU load. So it's not that interesting, but the important part here is we have to keep track of what's going on at all times, whether that's through queries per second or users that are coming in, and what's our fail rate, what's success rate of the APIs and of the actual streaming application. It depends on, of course, your business and what you're trying to do. But you also need testing. So if you all remember back to January 13th, which I'm sure will live in infamy for those who live in Hawaii, there was a ballistic missile threat inbound to Hawaii. It was not a drill, apparently, but it ended up being a false alarm. Now, if we don't consider the durability of our systems and the reliability and the monitoring with the testing, I want this to be a very clear case into what can go wrong. You can cause panic for hundreds of thousands of people at a drop of a hat, where they think their entire life is coming to an end. Now that might be a little bit boisterous, given that your site that serves cat memes may not be quite as pivotal to life, but let's just assume that somebody in here is actually doing something that would scare the living jeebus out of everybody. So your website is down across the world now because you didn't bother to do durability and reliability. And technically, that's all I've got.
What are the key things when you think of durability, your approaches to ensuring you have durability?
Yeah, so the question was, what do I think of durability and how to ensure that? Sorry, I think I'm running a little bit early here. So when I think of durability, I think of you have to make sure that your input is coming in at all times, and if it's not coming in, that you have some fallback condition. And because there needs to be resiliency, you've got kind of different workflows coming in. You have to worry about where the data is coming from ultimately, where it's going to. And in my case that I was trying to illustrate here, what I focus on for the durability on my part is making sure that when we make the changes to the API, because that's the main point that actually affects customer experience, whether the Kafka queues are working, whether any of that is working, is not as important to me as the ultimate change to the website. And so the durability is really built in there to make sure that whatever rules are created, they have either a quick expiration or there's some sort of pulse check, or something like a dead man switch, if you will, where if it's not getting a new rule in, then it just falls back to its default condition. So that would be the ideal, is some sort of system where you have, where you're thinking about the ultimate experience that really matters, and making sure that the customer doesn't get negatively or adversely affected by that. Does that help a little bit? Okay. Yeah. Yeah, so the question, or the follow-up to that was with regard to Kubernetes and the deployment strategy. So this is all in Kubal. Yeah, I could have mentioned that. Yeah, isn't that awesome? So anyways, yes, this is all running on Kubal. And right now, what that means is Spark 2.3 is so new that I'm using a beta version of their deployment on my own cluster that I'm trying to get other people not to use. Because the point of it is Spark 2.3 is so new that there's very little access that can be had there. So that's why durability is especially important for me, because I know that what I'm working with is so on the absolute cusp of brand new and bleeding edge, cutting edge, whatever fun terms you want to fluffy throw out there. So yeah, does that help a little bit? Okay, cool. Hold on. Go ahead with the microphone.
Right. So how do you make sure that you don't process the same data twice in case of the failure? So when you, for example, reading the stream and writing into some persistent storage, you usually write the metadata all together with it, like like the Kafka S3 Connect doing. You just basically write.
Sorry, what?
S3 Connect.
Okay.
Kafka S3 Connect,
Yep.
like how it handles how it basically provides the idempotency. It writes the offsets into the name of the file. So after the failure, it knows basically where to start from. In case you are writing directly to some kind of API,
Yep.
how do you basically handle that situations?
Yeah, so in that situation, we actually have two different options available to us. So right now, it's written so that we can just rely on the API to check to make sure that we're not creating rules that are in conflict with each other. So the API will handle that part. It'll say, okay, I've got these rules, because ultimately there are conditions that it needs to match. So these are pre-built APIs that exist for other functions of the business. So there are only certain rules that can be created. This is not some new API that I created. This is me just consuming an existing system. And so that's where I rely on is I don't have something like, I can't write out the offsets to the API and have it do something with that. And I could potentially check that, but that would add an additional layer to my side to make sure that the offsets are intact. So I don't have any way right now to stop it from you writing the same rule out twice or you processing the same data twice. What I instead rely on is the API itself, when it receives the data, to say what rule is going to take effect. And so it has a hierarchy of rules, of chains that it will follow.
Hello?
Yep.
So basically you are relying on the basically consumer. Consumer should take care about his part, right? So even if you provide the same data twice,
Yep.
it will not break anything on the consumer
Correct.
side. Okay, I see.
Because ultimately I'm writing out the rules in a very structured, specific way that's that API can only ingest it in a way. Does that make sense? Sorry. Okay. Yeah. I think she had a question. I think she was the first one to.
When you have machine learning algorithms in your real-time decision making, where does your machine learning model sit? Is it from the Spark ML for your streaming, or you pre-train it and load it to Redis? And if you are using XGBoost, how does it work? Because I think XGBoost is a pretty large model.
Yeah, no, fair question. So our models right now are all pre-trained. Then we save them off and make sure to run them in the most streamlined possible way, using actually pretty fast instances on Amazon that ultimately will make it so that we don't have, there is some cost, of course, so we can't do it necessarily in those milliseconds response time that I would want. Hopefully we can get there at some point, but everything is pre-trained and then cached so that we can serve that model in real time. What I should have put in here that I didn't get to was an example of how you actually do that, but I didn't put it in here because really you apply it in the same way. You just add a transform method on a stream instead of on a static data set, on a static data frame. Does that answer your question? Okay.
Thanks, Garren. Actually, that was pretty close to what I was concerned about. And so really, I want to drill into what's the boundary or the transition between batch and streaming here? Because I'm all for dynamic model deployment, so it sounds like you folks are using the stream as kind of your request system, the way you're kind of deploying the model.
Yep.
So the question I guess I would have is, so we do something very similar.
Yep.
But I guess syntactically, why I have zero experience with Spark Streaming, but is there a way to kind of set it up so that you could do it in batch or streaming at the same time? Is the syntax, at least in Scala code, similar? What are your thoughts about this transition? Because we don't always need the power of streaming, right?
No, that's totally fair. Streaming is just, it's awesome from the context of you can make those changes really fast. And fundamentally, that's one of the reasons why I have especially taken to using Spark streaming and structured streaming as opposed to Flink, particularly, even though I know a lot of other people use it, and I know that it's popular out there for streaming applications, is because I come from a Spark background, and more importantly, I love some of the context of how Spark works. So I know that in this case, the syntax is basically identical. I could take the exact same code that I used. In fact, I can go back to that. If I go all the way back to my Python or my Scala code, so literally all of this code, if I had a data frame there that was of a normal data frame and not a streaming data frame, which technically Spark doesn't even differentiate if you look at the return value of the actual object, is the type, it just says org.apache.spark.sql.dataframe. Even for a streaming data frame, technically, that is the object type. So all of this code would work just the exact same way. And this would all be lazily evaluated because I'm not doing any actual actions on it. Yes, so the question was you could write a function that would consume both the data frame of the static variety and the streaming. Yes, absolutely. That's one of the coolest parts about Spark that I love especially, is that you can intermix them and do whatever you want with either one and use the exact same code, because fundamentally they're both I should put a caveat there. You can use the exact same code, but there are some limitations to what you can do with a stream versus what you can do with with static. For example, date time. If you try to run a current time on it on a stream, it'll fail because it can't ensure that it's up to date and it's correct. There's a specific limitation on that one, and there are a bunch of other ones too. But that fundamentally the same code does apply. Does that make sense?
Hi. Thanks for presenting. I have a quick question. So you presented the streaming thing, and first question now, is it like in production somehow, or are you guys testing? And second one, if yes, then you join these two flows of streaming. Does it help to boost accuracy of your recommendations or whatever, like predictions?
Yeah, so first question, no, it's not in production, full production, because in order to use Spark 2.3 on Qball, that stuff takes time to develop the full deployment of that. So right now it's still considered beta, and so none of us really want to push the limit on that. Not to mention we're running a streaming application, so we really need to be concerned about the longevity of that stream over time and make sure that all the durability is put into play. The rules API that I had mentioned is there, and so we do get to mess with that and make changes, but we haven't been able to put this. We don't want to put it into play because it has such a huge impact on the business until we have full confidence in all of the systems that come together. So right now it's just been in testing, and it's ready in a lot of ways to go to production, but we need to be even more sure of it. And the second question. Yes. Yes, no, this, it's not, I can't divulge what it's doing, but I can say that what it's doing fundamentally is extremely powerful. And so it boosts our ability to go from option, it makes our ability to really adjust to what the customer wants to see and will ultimately click on better by a lot. So the impact is substantial to the customer experience in a way that no other system that we've even seen has been able to really accomplish. Yeah, that's fine.
I don't understand that comment though.
Okay.
Sorry, I don't mean to push you here.
No, that's fine.
So what's the difference between having just a normal model deployment setup where you just hit it with requests and this? I mean, since you're just deploying, I'm not sure how you're making performance.
For,
And assuming that you have a Heiple Architecture deployment setup, like XPU is just for Schema platform.
yeah.
And they have specific SLAs. Like, what I'm trying to understand, like, what's the big breakthrough?
The big breakthrough here is that we're able to take two different data sets and act on those using our model, and more importantly, act on it in a way that directly impacts the customer experience right then and there. Does that make a little bit more sense?
I'm sorry, I think we can talk offline.
Yeah. No, I want to understand what I'm not getting across, I guess, better.
You just can't immediately react on the user action, right?
Yeah.
With streaming, but I think the original question was about accuracy, like how precise your result is. I think from that perspective, like, it really doesn't matter. As long as yeah, right.
Model's good,
Right.
it's trained
Yeah.
well.
So we're coming up with 2 more minutes left.
Okay.
I think this is a great discussion. We have plenty of time in the hallways. I think just take that
Yep.
offline. There was one more question. I think we have time for one more question, and then we'll wrap it up.
When you move to streaming, you talk about how the data should not overflow and that problem. So how does autoscaling works in the streaming application? So like if your streaming application is live, are you running with the max hardware, or are you upscaling or downscaling based on your input or output queue size?
Yeah, no, excellent question. So auto-scaling is not something that usually should be done with structured streaming. So you can do it. I think it is an option. I'm pretty sure it has some warnings, even more verbose than my warning here. But no, you don't want to have usually any sort of auto-scaling if you can avoid it, because I just wouldn't want to rely on that. But however, I would say that because it's running 24/7 and because it's processing smaller chunks of data, you don't usually need a huge amount, and the pool size that you can have is actually pretty substantial. When you think about if you have, say, 3 executors, three JVMs that are running each with, say, 40 gigs of memory, and you've got 8 cores, so now you've got 24 cores and 120 gigs of memory, you can put a lot of data into memory and leave it there on both sides. So you could say, even look back an hour, and you'd still be able to have like potentially millions of records on both sides and be able to do those joins and make those changes to any upcoming customers that would be unaffected otherwise. So if you did just a batch job, you'd be waiting an hour, then you'd be processing the last hour, and then customers would be going forward. But in this case, hopefully to Sean's point more, is you're going to be taking what's exactly happening now from 2 different sets, including one third-party data set, and making those changes that your user came in and saw option 1 at the top, but because you're able to make that change in real time, the very next search that followed similar criteria, they immediately got option 2 first, because that's what we've learned is actually more relevant to that search and that user and that behavior, that pattern of behavior. Does that answer your question? Okay, sweet.
Cool. I think we'll conclude. Thanks a lot, Garren. Wonderful talk. Thanks, everyone.